doing lab 5, and I'm going to show you a little bit about the debouncing circuit and just show you how I built it and how it should be functioning once you get it going. I'm using the SN7438N NAND gate chip. Here is what that looks like. Maybe I can get it to focus. There we go. That's what that looks like. I've got it on the breadboard like this. It's straddling the spine of the breadboard so that we get access to all the pins. We're gonna use 2 NAND gates from this quad NAND gate chip. So this NAND gate actually has 4 NAND gates on it. I've printed out the specification sheet for the SN7438N, and you see the pinout here. We've got 14 pins. The NAND gates look like this. So 1A, 1B, those are the 2 inputs for NAND 1, and the output is 1Y. So 1A, 1B, 1Y are the inputs and output, and then 2A, 2B, 2Y, also on that same side, are the inputs 2A, 2B, and then 2Y output. So the inputs and outputs on one side can be used. That's what I'm doing here. I'm actually using pins 1 and 2 as the input to NAND 1, and then the inputs 4 and 5 to the input to NAND 2. The outputs are pins 3 and 6 on that side. And I actually connected it up so that those numbers correspond to the rows on the breadboard. And there's kind of a mess of wires here. But I also connected up the pull-up resistors. I made the plus on this side of the breadboard, 3.3 volts coming out of connector A. So connector A's got 3.3 volts, which that brown wire is connected up to. And then the blue wire is connected up to 5.5, 5 volts, which is the other positive rail. And then the negative rail is the black, which is connected up to the analog ground. So those are our supplies. We need to supply power to this integrated circuit chip. So we've supplied power to the rails. We jump off the rails to power the chip, and we have our pull-up resistors as well to our logical digital high, which is our 3.3 volts. Yes, okay, so we've got all that. We've also got the switch here. So we've got a single pole double throw switch with the 3 connections that are kind of hard to see, but there are 3 rows of the breadboard connected here. So they are 19, 20, and 21. The common connection for the switch is 20. I've got that's connected to digital ground, and I've got the normally open and normally closed pins pulled up to our logical high level. We have those pull-up resistors, and then we've got them also connected to the normally open and normally closed are connected to our 2 NAND gates as shown in figure 516 in the lab exercise. Remember this, I should fix that, but DIO 0 connects to beta. This is a typo instead of connecting to alpha as is shown here. Otherwise, I just connected it up like that. I also set up the oscilloscope to look at the output of my beta NAND gate, and the output is going to be high normally, and then it's going to be drawn low when I press the button. So this debounced button, when I press it, should bring that low. Now, if I unroll, if I auto trigger, it's high, and if I press the button, I'm pressing the button here, it'll draw the channel low, just like we want. We want a nice clean transition without the bouncing. We want this to be debounced. So in order to capture that, it's gone really quickly. So how I set this up, I've got it set up to be 10 microseconds per division in time. If I change it to normal and I trigger on, I've got the trigger menu up here by hitting the trigger menu. It's triggering on channel 1, on edge, on down slope, because we're going to be drawing to the low level, and we can set the level to be anywhere between 0 and 3 volts. Should be okay. Middle is probably best. And in normal mode, it's going to wait for a trigger. It's going to wait for that, and then it's going to hold off. I set the hold off to be pretty high, so 93 microseconds, so quite a while before it gets re-triggered. So if I press the button, we see a nice clean transition happen, and the oscilloscope holds that. If I press it again, we get a nice clean transition again. Press it again, nice clean transition. We just keep getting nice clean transitions without bouncing, which is great. That means that our interrupt request will only be sent once each time we press the button, which is what we want. Of course, I don't have the LCD screen and keypad plugged in at this point to the B connector, which that will need to be connected in order to get it to work, because we want to print in our interrupt service routine. We want to print to the LCD, but also remember we want to disconnect the motor board for this lab exercise. But I just wanted to show you my my debounced circuit and what it looks like with the NAND gate chip, with the switch, and how to connect up the pull-up resistors and all that. These pull-up resistors are all 2.2K. Just have a bunch of them here, but there's a drawer in the cabinet with the 2.2K. So yeah, I printed out some sheets. These are at each station, so that you can wire up your own circuit. Okay, good luck. Take care.